Hi, my name is Vinay, and in this video I will demonstrate the working of this basic vertical arm controller for rotary inverted pendulum setup. So in the previous video we have seen the 3D model of the rotary inverted pendulum. So this is the 3D mechanics editor created 20sim model of the pendulum setup. If you double click on this, it will open the 3D mechanics editor where you can observe how this is constructed. So you have the vertical base and the horizontal shaft and the vertical arm. On top of it there is a sphere attached to it. A disturbance arrow is being added to it so that you can add a disturbance to it. Okay, so this is a force actuator which will apply it on the sphere to create any kind of disturbance. So you can change the mass of the bodies and simulate accordingly. So 20sim can create the model of it by clicking on this button, generate 3D model, and I've already done this, so I don't make a change in this. For the DC motor I'm using an velocity actuator which is connected through a gearbox followed by a spring damper. So this is the input to the 3D model, because 3D model has an actuated joint of the horizontal shaft through which it controls the position of the vertical arm. The 3D model gives two outputs. One is the arm angle, the vertical arm angle, and the motor angle. So these two are fed to encoder gain blocks, which converts the output in number of pulses and given to these blocks. This block is the controller block. So if you go inside, you will find that there is a basic PID controller who takes the feedback from the vertical arm, passes through an gain block, attenuate block, and this guy converts the counts into degree outputs of the angle. So this guy will give the degree output. So this output is given to an plus minus block who subtracts this feedback from a constant who represent the set point of the vertical arm, which is 0. So if you go inside, you find the constant value is 0. So this is representing the vertical arm angle. Subtracted value is called as error, which is given to a PID controller who decides that how proportionally and integral and derivatively he has to control the position of the DC motor. There is a limiter who limits the PID output to plus minus 1 range, that is the 100% steering of the DC motor in both directions. The output of this block is given to a switch, and finally to the pendulum output of the motor. Now why there is a switch and why this connections? That is because to keep the pendulum setup safe from any kind of mishappening or wrong control of the setup. So in case the vertical arm of the pendulum goes below or beyond any certain range of values, this output, which is we call as active output, is enabled. So if the active is high, the switch will be disabled, and also the controller will also be disabled, so that you can safely turn off the motor. So if you go inside this enable block, you find that phi, or the angle in degrees, is 1 and 20. So if the pendulum angle is between this angles, okay, so if it is enabled only when it is less than 0, less than 1, and it is disabled when the angle falls back to more than 20 degrees. So if the vertical arm goes below 20 degrees, it will turn off the controller and keep the setup safe. So that is why this block is being added to the design. And also this guy has an offset, so that there is an offset added to this block, minus 180 degree, so that the controller only starts when you are at 180 degree offset from the bottom side. And these are the force actuator which acts as a tip disturbance, and this is a friction model for the vertical arm. So let's start simulating this model. So just play the simulation, and you can see that the model is executing its simulation, and now you can play the real-time animation of the simulation results. So you can see that from the angle, so there's a small disturbance coming up, so there's small jerks are there in the vertical angle, and horizontally the motor was shifting here and there a little bit. So any small disturbance will keep on rotating the horizontal shaft. So let's download this model and verify how it works in the hardware. So go to Tools, Real-Time Toolbox, C Code Generation, select the 20sim template and the controller model. Select the rotary inverted pendulum template. So you can see that the controller board has detected the software through the LAN network. Now go to connect block. So okay, it opened the previously saved project, hence we see previously connected output, but no problem, I will show it again. So the encoder 1 motor input will be coming from motor quadrature counter. The ARM encoder 2 ARM input will be coming from ARM quadrature counter. And the output pendulum motor will be connected to pendulum motor output. Click OK and compile. So once the compilation is over, you can go to command block. You can see that the frequency of execution of the model is 500 Hz. So let it be like that. So we will also log the output of the pendulum arms. So we can select the encoder arm output, this block, and the encoder motor output, this one, and we'll see how does it works and how is the responses. Okay. So the pendulum, the enable block has the setup to, I'm just rotating anti-clockwise to loosen up the wire. So the model has been designed in such a manner that unless you don't bring the pendulum upright on the top side, it will not activate the controller. So let's run this. So I'm running with log model. So you can see the pendulum is not responding. That is because it's been disabled. So you have to lift it up clockwise till the top side. So you can see that the controller comes in action and he controls the pendulum. So I just add a disturbance so you can see that he's trying to control it, and I stop it. Okay. So if you try to fall it down, so it will stop. Yeah. So you can see the responses of these plots. So you can see that it was keeping the value well stable under a range. So it is like the 1 plus minus 1 degree of angular disturbance he was getting. Let's run it again. So if you run anti-clockwise, so you can see that the controller is not coming in action because that is, the angle is in the negative direction. So you have to put it on the clockwise and you see the controller comes in action. If you add too much of disturbance, the motor will disable itself. Like for example, I added disturbance, so you see if the angle falls too much, it will stop. But as of now, you can see that he is able to take a good amount of disturbance. Okay. So you have to repeat the same experiment at your classrooms and you can understand the effect of the control algorithms. Thank you very much.